Welcome back to the session on numerical methods. In the previous session, we derived Newton-Raphson formula. Now, here I shall discuss the geometrical interpretation of Newton-Raphson method. Consider the graph of y equal to f of x. We have to solve equation f of x equal to 0. By the location theorem, first we find an interval in which the root lies. Suppose a b is an interval. Now, we take x naught as an initial approximation of the exact root. Let x naught is here. Then we can mark the point x naught, f of x naught. We draw a tangent. We draw the tangent at this point, at the point x naught, f of x naught, which will meet the x axis. The meeting point on the x axis can be taken as the first approximate value of the given equation, or first approximate value of the root of the given equation. Say, let it be x 1. Now, we evaluate f of x 1 and mark the point x 1 f of x 1. We draw the tangent at this point, which will meet at the x axis. The meeting point can be taken as, say, x 2 can be taken as the approximate value of the exact root. Now, again we evaluate f of x 2 and find the point x 2 f of x 2 on the curve and draw the tangent, which will meet the x axis again. Proceeding like this, we will get, after a finite number of iterations, the point will become very close to the x axis, which is the geometrical interpretation. The equation of tangent is y minus f of x naught is equal to f dash of x naught into x minus x naught. This is the equation of the tangent at the point x naught f of x naught. Since the tangent meet on the x axis, at the x axis, on the x axis, we can put y equal to 0, that is, on the x axis y equal to 0, we will get minus f of x naught is equal to f dash of x naught into x minus x naught, or x minus x naught is equal to negative of f of x naught divided by f dash of x naught, which implies x equal to x naught plus, sorry, x naught minus f of x naught divided by f dash x naught. Which is taken as the iterative formula for the Newton-Raphson method. We find this x, say x 1, by putting x naught, and again by using this x naught we will find better approximation x 2 and so on. This is the geometrical interpretation of Newton-Raphson method. Now, we have to see the convergence criteria for Newton-Raphson method. The Newton-Raphson formula is x n plus 1 is equal to x n minus f of x n divided by f dash of x n, which is of the form x is equal to phi of x, because x n plus 1 is the approximate value of the exact root x and x n also the approximate value of the exact root x. Therefore, we can express this formula like this, that is x equal to phi of x. Here phi of x is equal to x minus f of x divided by f dash of x. For fixed point iteration, we have the convergence criteria is modulus of phi dash of x is strictly less than 1. That is, here phi dash of x is equal to derivative of x is 1 minus, we use the quotient formula for derivative, that is in the denominator f dash x square, in the numerator f dash of x into derivative of f is f dash of x minus f of x into derivative of denominator, that is f double dash of x, which is equal to f dash of x square minus, this is f dash of x square, negative of negative is plus f of x into f double dash at x, all divided by f dash of x square, which is equal to, on simplification, f dash of x whole square minus f dash of x square cancelled, that is equal to f of x into f double dash of x divided by f dash of x square. This is phi dash of x. Now, mod phi dash of x less than 1 gives modulus of this f of x into modulus of f of x into f double dash of x divided by f dash x square is less than 1, which implies modulus of f of x into f double dash of x divided by modulus of f dash of x square by the property of modulus, we can split like this. This implies modulus of f of x into f double dash of x is strictly less than f dash of x square, mod f dash of x square, modulus of f dash of x square, that is f dash of x square. This is square, therefore modulus is f dash of x square itself. This is the convergence criteria for Newton-Raphson method. Now, I will explain the order of convergence in the Newton-Raphson method. Order of convergence. Let alpha be the root of the equation f of x equal to 0. Alpha be the root of the equation f of x equal to 0. Then f of alpha equal to 0. F of alpha is equal to 0. Let x n and x n plus 1 be the approximate values of the exact root after n and n plus 1 iterations respectively, and let epsilon n is equal to x n minus alpha and epsilon n plus 1 is equal to x n plus 1 minus alpha. That is the error, the difference between the approximate value and the actual value. If f of x equal to 0 is expressed as x equal to phi of x, we can write x n plus 1 is equal to phi of x n in general. That is equal to phi of x n is epsilon n plus alpha or alpha plus epsilon n, a function of alpha plus epsilon n, which is equal to phi of alpha. Here we use the Taylor's theorem. By using Taylor's theorem, we can write this as phi of alpha plus epsilon n divided by 1 factorial into phi dash at alpha plus epsilon n square divided by 2 factorial into phi double dash at alpha plus etc. That is equal to, here alpha is the root of the equation f of x equal to 0. This f of x equal to 0 is x equal to phi of x. We just rewrite this equation f of x equal to 0 as x equal to phi of x. Therefore, phi, since alpha is the root of the equation, phi of alpha is equal to alpha itself, that is alpha plus epsilon n by 1 factorial into phi dash at alpha plus epsilon n square by 2 factorial into phi double dash at alpha plus etc. Therefore, epsilon n plus 1 is equal to, here epsilon n plus 1 is x n plus 1 minus alpha, where x n plus 1 is equal to the series. We substitute this x n plus 1 here, that is epsilon n plus 1 is equal to epsilon n plus 1 is equal to x n plus 1 is this alpha plus epsilon n by 1 factorial into phi dash of alpha plus epsilon n square divided by 2 factorial phi double dash alpha plus etc. That is equal to, epsilon n plus 1 is equal to x n plus 1 minus alpha. Alpha minus alpha is equal to 0. Therefore, this is equal to epsilon n by 1 factorial into phi dash of alpha plus epsilon n square divided by 2 factorial into phi double dash of alpha plus etc. That is equal to epsilon n by 1 factorial into phi dash of alpha plus epsilon n square divided by 2 factorial into phi double dash of alpha. After this term, that is the next term is epsilon n cube divided by 3 factorial into phi triple dash of alpha and so on. We neglect the remaining terms because epsilon n is very small, that is why the higher powers of epsilon n are tending to 0. Therefore, we can neglect the remaining terms. We will get epsilon n plus 1 is equal to epsilon n by 1 factorial into phi dash of alpha plus epsilon n square by 2 factorial into phi double dash of alpha. Now, we find phi dash of alpha and phi double dash of alpha and substitute in this, that is here phi of alpha is equal to x minus f of x divided by f dash of x. Then phi dash of phi of x is equal to this x minus f of x divided by f dash of x. Now, phi dash of x is equal to f dash x square into phi dash of x equal to 1 minus f dash of x into f double dash of x, sorry, f dash of x minus f of x into f double dash of x. That is equal to, on simplification, we will get f of x into f double dash of x. Divided by f dash of x square, because okay, this now this is phi dash of x. Phi dash of alpha is equal to f of alpha into f double dash at alpha divided by f dash of alpha whole square. But f of alpha equal to 0, because alpha is the exact root of the equation f of x equal to 0. Therefore, f of alpha equal to 0 implies phi dash of alpha equal to 0. The reason is f of alpha equal to 0, as alpha is a root. Now, we differentiate again, that is phi double dash of alpha x is equal to f dash of x raised to 4 f dash of x square into derivative of this, that is f of x into f triple dash of x plus f double dash of x into f dash of x minus f of x into f double dash of x into derivative of the denominator, that is 2 times f dash of x into f double dash of x. Now, phi double dash of alpha. Here f of alpha, if we substitute alpha, we will get here f of alpha, which is equal to 0, because alpha is the exact root. That is why this term is 0. Here also f of x, this term will become 0. The remaining term is f dash x square into f double dash x into f dash x divided by f dash of x raised to 4, sorry, f dash of alpha square into f double dash of alpha, f dash of alpha divided by f dash of alpha raised to 4. That is equal to, this is f dash of alpha square into f dash of alpha is f dash of alpha whole cube. In the denominator, f dash of alpha raised to 4. On cancellation, we will get phi double dash of alpha is equal to f double dash of alpha divided by f dash of alpha. That is, phi double dash of alpha is equal to f double dash of alpha divided by f dash of alpha. Therefore, we will get epsilon n plus 1 is equal to, we substitute phi dash of alpha and phi double dash of alpha in the expression of epsilon n plus 1, we will get 1 by 2 into f double dash of alpha divided by f dash of alpha into epsilon n square. That is, epsilon n plus 1 is equal to f double dash of alpha is a constant, f dash of alpha is a constant, 1 by 2 is a constant. Therefore, this quantity is a constant, let it be k. into epsilon n square. Therefore, the rate of convergence, the order of convergence for the Newton-Raphson method is 2. That is, Newton-Raphson method is of quadratic order. We can conclude Newton-Raphson method is of quadratic order because here the square happened. Now, we shall work out a problem. The question is, find a real root of equation 3x is equal to cos x plus 1. Here, this equation can be written as 3x minus cos x minus 1 is equal to 0. 3x minus cos x minus 1 is equal to 0, which is of the form f of x equal to 0, where f of x is equal to 3x minus cos x minus 1. F of 0 is equal to minus 2, which is negative. F of 1 is equal to 1.4597. 1.4597, which is positive. Therefore, by the location theorem, we can say that there is a root in between 0 and 1. We choose x not equal to 0.6. Here, f of 0 equal to minus 2, f of 1 equal to 1 point something. If we compare these two values, this value is closer to 0 than this value. Therefore, we choose x naught as 0.6, which is near to 1. Then, by Newton-Raphson formula, we have x n is equal to x n plus 1 is equal to x n minus f of x n divided by f dash of x n. Here, f dash of x is equal to 3 plus sin x, then the RHS become x n plus 1 is equal to x n minus f of x n is 3 x n minus cos x n minus 1 divided by f dash of x n is 3 plus sin x n, which is equal to 3 x n plus x n sin x n minus 3 x n plus cos x n plus 1 all divided by 3 plus sin x n. That is equal to 3 x n minus 3 x n is 0. The remaining part is x n into sin x n plus cos x n plus 1 all divided by 3 plus sin x n, which is the iterative formula in this problem. Now, we put x naught equal to 0.6. We will get x 1 as x 1 is equal to x naught into sin x naught plus cos x naught plus 1 divided by 3 plus sin x naught, that is equal to, on simplification, we will get x 1 as 0.6071. If we put x naught equal to 0.6, we will get x 1 as 0.6071. Now, we put this x1 equal to 0.6071 in this formula, we will get the second approximation as x2 is equal to x1 into sin x1 plus cos x1 plus 1 all divided by 3 plus sin x1. One simplification, we will get 0.6071 again. Approximately they are equal. Therefore, we can conclude that the approximate root of the given equation is x is equal to 0.6071. Now, another problem, we can use the Newton-Raphson method to find the square root of a number. Suppose we have to evaluate root of 12 using this Newton-Raphson method. We take x equal to square root of 12, then on squaring we will get x square equal to 12, which implies x square minus 12 equal to 0, which is of the form f of x equal to 0, where f of x is equal to x square minus 12 and f dash of x is equal to 2x. Then by using the iterative formula for Newton-Raphson method, we can write x n plus 1 as x n plus 1 is equal to x n minus f of x n. F of x n is x n square minus 12 divided by f dash of x n, that is 2 x n, which is equal to 2 x n square minus x n square plus 12 all divided by 2 x n, that is equal to 1 x n square plus 12 divided by 2 x n, which can be written as 1 by 2 into x n square by x n is x n plus 12 by x n, that is x n plus 1 is equal to 1 by 2 into x n plus 12 by x n, which is the iterative formula in this problem, that is to find root of 12. X n plus 1 is equal to 1 by 2 into x n plus 12 by x n. Now, if we put x equal to 0, we will get minus 12, which is negative. F of 0 is negative, f of 1 is also negative, f of 2, that is 4 minus 12 is negative, f of 3 is 3 square minus 12 is negative. We will find an interval of approximation, that is f of 3 is equal to 9 minus 12, that is minus 3, negative. F of 4 equal to 16 minus 12, that is 4, which is positive. Therefore, we can conclude that there is a root in between 3 and 4. Here f of 3 is minus 3 and f of 4 equal to 4. Minus 3 is closer to 0 than 4. Therefore, we can choose the arbitrary value x naught as very near to 3. We take x naught is equal to 3.5. Choose x naught equal to 3.5 arbitrarily. 3.5 is a number in between 3 and 4. Therefore, we can write, we will get x1 is equal to 1 by 2 into x naught plus 12 by x naught, that is 3.5 plus 12 by 3.5, which is equal to 3.4643. Similarly, we will get x2 is equal to 3.4641, x3 is equal to 3.4641 approximately. Therefore, we can conclude that the approximate value of the root of this equation x square minus 12 is 3.4641, correct to 4 decimal places. That is, the square root of 12 is equal to 3.4641 approximately. Now, let me conclude this session. In this session, we discussed the geometrical interpretation of Newton-Raphson method, the convergence criteria for Newton-Raphson method, and the order of convergence in the Newton-Raphson method, and we solved 2 problems. Thank you for watching this session.